Find the current ID using LCM equations of this NMOS transistor. We are given the following parameters: threshold voltage equals 0.4 volts, transconductance parameter Kn equals 1 milliamp per volt squared, bulk threshold equals 0.2 volts to the 1/2, channel length modulation equals 0.1 volts to the -1, oxide capacitance equals 1.004 microfarad per centimeter squared, surface potential equals 0.88 volts, width equals 1 micrometer, and length equals 0.1 micrometers. So first, as always, we identify the four parts of this NMOS transistor. We have the gate on the left side, drain on the top, source on the bottom, and body or substrate on the right. Let's first test to see if this device is on. We need to find VGS and see if that's greater than VTN, which is not VTNO. So VGS equals VG minus VS. And we can see at the gate there is a 1 volt potential at that node. So it's 1 volt minus the source, which is ground, 0 volts, which equals 1 volt. And to see if there's body effect, we must test whether or not VSB exists. And that is equal to VS minus VB, which is 0 volts minus -1 volts, since the body has a -1 volt potential, and that'll give you 1 volt positive. Thus, body effect does exist in the circuit, which will make us add one little part to the equation. So VTN now has to equal VTNO plus gamma times square root of absolute value of 2 phi f in case it's negative, plus VSB minus square root of absolute value of 2 phi f again. And if VSB didn't exist, or was 0 in other words, then this entire term would cancel out to be 0, which would get rid of gamma, which would mean that VTN just equals VTNO. However, since VSB is 1, we need to account for it. So VTNO was 0.4 volts given, plus gamma 0.2 volts to the 1/2, times parentheses square root of 0.88 volts plus 1 volt minus square root of 0.88 volts. This gives you a threshold voltage equal to 0.487 volts. Now comparing that to VGS, which we again found to be 1 volt, we can see that it is greater than VTN. So the device is on. Now to see what mode it's in, we need to find VDS sat. So if VDS is greater than this, then it's in saturation mode. If it's less than this, it is in triode mode, or linear, some might call it. And VDS sat, given the long channel model equation, is VGS minus VTN, or 1 volt minus 0.487 volts. And that equals 0.513 volts. VDS, on the other hand, equals VD minus VS, and that equals 1 volt, which is on the top here, minus ground, and again, that's 1 volt. Comparing that, it is obviously greater than VDS sat. As I said before, in this situation, we see that it is operating in saturation mode. Now to find the current in the drain here, I'll denote it as ID sat, and that equals Kn over 2, parentheses VGS minus VTN, close parentheses quantity squared, times the following: 1 plus lambda times VDS minus VDS sat. So as to account for channel length modulation once more. Plugging in the numbers, we see that ID sat equals 1 milliamp per volt squared, or 1e negative 3 amps per volt squared, over 2 times 1 volt minus 0.487 volts, all of that squared, times 1 plus 0.1 volt to the negative 1, times 1 volt minus 0.513 volts, close parentheses twice. And putting this in the calculator, you get your final answer of 138 times 10 to the negative 6 amps, which is equivalent to 138 microamps. If you have any questions, please leave in the comments below, and good luck.